In order to understand the prisms that we're going to be studying in this chapter, I recommend that you make yourselves a net diagram of each of them, and then you build them up to have 3D pictures. I think a good idea would be to have one that is flat like this, and one that you build up. The measurements on my rectangular prism that I'm going to build go 5, 5, 5, 5. These are all 4, 4, 4, and that'll also be 4 centimeters. And then my two side flaps are 3 centimeters and 3 centimeters respectively. There's one that's got a few folds in it. What's going to happen is that I'm going to fold on most of the dark lines. And when I put them together, I'm going to get something that looks a lot like a box. So that is now a rectangular prism once it has been put together with sticky tape or anything else that you think would work to be able to make it into a 3D shape. This is the net diagram for a right-angled triangular prism. We have two right-angled triangles, 5, 4, and 3 centimeters on either side, and then the height of the prism is 6 centimeters. So that's going to be 3, that's going to be 4 to map onto that, and this one's going to be 5 to eventually connect with the hypotenuse of the right-angled triangle. When that one is built up, it's going to look a little bit like this. Where you have two right-angled triangles, one on the top, one on the bottom, and then you've got 3 different rectangles that also make up this shape. The cylinder is by far the most complicated shape to understand when it comes to surface area. This shape can be made using 2 circles and a rectangle. The circles can be anywhere along. I've used a glue stick for this shape. It is exactly 3 centimeters in diameter. And then to get this size here, that needed to be 2 pi r, or pi times the diameter. So that's why it's a strange number with a decimal point there. The height is 6, the same as the other prisms that we're going to be making. When you build that one up into a 3D shape, you need to bend the 2 circles down and take the rectangle and curve it around. And that is why this distance around here is the same as the circumference of the cylinder. What I recommend you do before building up your rectangular prism is to identify that there are 3 pairs of identical rectangles. So the reason I've called this one A, it's 5 by 4 centimeters, and this one A is because it's also 5 by 4 centimeters. The 2 rectangle A's are not together. They are not touching each other in this net diagram, and they won't touch each other in the final product either. The B's are my 5 by 3, and the C's are the 3 by 4. It doesn't matter which ones you name, A, B, and C, but what it does matter is that your 2 A's are the same, your 2 B's are the same, and your 2 C's are the same. When you stick it all together, you should have something like this. An A, then a B, then an A, then a B, and then a C over there, and another C on that side. And that will help you understand how to calculate surface area a bit later. Before putting together your triangular prism, I also recommend that you label the different rectangles A, B, and C. Now, they won't always be 3 different rectangles, and neither will that be the case with a rectangular prism. But what I think you need to understand is that that A has this measurement of 3. The B rectangle has the measurement of 4. The C rectangle has the measurement of 5, and that 3, 4, and 5 are all mirrored on the triangles on both sides. When making up your cylinder, I recommend, because it is 3 centimeters in diameter, which is roughly the same as the glue stick, and you probably used a glue stick to measure, to get that curve, put it around like that. Then put quite a bit of tape on it and slide it off. Alright, now it's a matter of getting the circles to also play ball here and stick properly. It is quite tricky, but the idea is just to be able to see there is a rectangle that has the circumference of the circles as its length, and that's how it maps on when you put it all together. When you're done, it'll look something like this, and the idea of having made these up is to have them as reference points to go back to as we study volume and surface area. And here are the final products together with their net diagrams. There's the rectangle with A, the 5x4, two of them, the B, which is the 5x3, and the C, which is the 3x4, two of those as well. The triangular prism has its rectangle A, which is 6x3, B, which is 4x6, and C, which is 5x6, and the two triangles that are both 3, 4, 5 Pythagorean triplet triangles, and the cylinder with its length the same as the circumference of the circle. Alright, let's talk a little bit about surface area. So when we calculate the surface area, it's a good idea to think of really stingy wrapping paper. If I was to wrap this Mazzina box in paper and I was to use the very bare minimum amount, then I would need to cover this rectangle and that one and that one and that one, and also that one and that one. And what that would amount to, and you can imagine if I open this box now, there will be tabs to use for sticking all the sides together. But what that will amount to is the surface area will be 6 rectangles all added together. 2 of them will be the same, those two. Then there will be 2 that are also the same but different to the first one. And then there will be the ones that are on the side that are also the same. And it's a good idea to have this in your head when you're trying to calculate surface area. Of course, a rectangular prism doesn't always have to have rectangles as its sides. This is a particularly interesting looking product. It's a South African ice cream company, and they make little cubes as their packaging. Of course, if you had to open this, it wouldn't be 6 squares like it is if it's an actual cube. In fact, I've got one to show you that has been opened out. It's quite fascinating. Look at that. But there are my 6 squares. That one, there, 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 and there. So all the other bits are just used to flap it up in order to make the box. The best product I can find to show you triangular prisms in real life is the Toblerone. The only thing that's different about the Toblerone compared to the triangular prism that we have made is that its triangle is equilateral. So this is all the same length. So that means that for this particular triangular prism, you're going to have rectangle A and another rectangle A and another rectangle A. They will all be the same. So let's pretend that the two sides that say Toblerone, those sides there are the same and the third one is different. Then with that isosceles triangle as the base, you'd have 2 rectangle A's and then just the one rectangle B. When it comes to cylinders, a good example is a tin, because we use them all the time and you're probably familiar with the shape. I have detached this label and I want to show you what happens to it. As it unravels, you can see how its length is the bit that went around the top of the tin. So what we are dealing with in terms of surface area is very much a rectangle where the length of the rectangle is exactly the same as the circumference of the circle. Perhaps a more familiar household product is a can of Pringles, where I'm going to fold, I can't take this one's label off, so I'm going to fold a piece of paper around it so that it works all the way around. And what you can see again now is that if I need to measure the length of that, it's going to be the same as the circumference all the way around the top of the tin. Let's talk a little bit about volume now. So volume, you probably remember from primary school, for a rectangular prism is going to be length times breadth times height. So it'll be the length times the breadth, and then we can call that one the height. You have three measurements for a rectangular prism. I've got here my 4, my 5, and my 3. So you multiply them all together and you've got the volume, whether or not you understand exactly what that means. What I'd like you to do for this chapter is I'd like you to develop a bit more understanding about what volume is. And volume is the amount of space that this takes up, okay? And we're also going to be converting those cubic centimeters or millimeters or meters into units that we would normally associate with liquid, like liters and milliliters and so on. So what I want you to understand is that however we put this thing down, and there it is, it's resting on the A, there it is, that's the one I'm putting down. Another way of looking at volume, I want to say area of the base, there it is, times the height of the prism, which will be this. Now, if I put this the other way around and I said area of the base times the height of the prism here, it would be exactly the same, because at the end of the day, with a rectangular prism, I'm just multiplying all three measurements together, and it works the same for my little green one. I can make A the base, I can make B the base, and I can also make C the base over there. So with a rectangular prism, it doesn't really matter which rectangle you call the base, but the concept of rectangular prism means that a rectangle has to be the base. And this is where it's different with a triangular prism. Because with a triangular prism, we've got to get our heads around the fact that the triangle is the base. However you put it down, you need to make sure that the triangle is the base. And so we're going to have, for volume, area of the base will be area of the triangle, half base times height. We've made this a right angled triangle deliberately so that your base and your height are really obvious. That's a right angle over there. So it'll be area of the base of the prism, which is half of this little base of the triangle times the height. And in the notes that follow, I'm going to distinguish between base of prism, which is the whole triangle, and base of the triangle. And I'm going to call this one the little base and this one the little height. And then we need to talk about height of the actual prism. And the height of the prism is going to be your 6. It's going to be the distance between this triangle and that one. So a way of looking at a prism, or way of identifying a prism, is saying, if you can sit it down on the table and the thing it sits on and the face that you can see, so its base and its face are the same, then it's a prism, or it's been set in a way that you can then calculate volume by knowing that the base is not one of the rectangles. And I could sit it like that. I could sit it on base B or C or A, but then I'm not going to get accurate readings, because when we talk about base in terms of volume, we definitely mean, for a triangular prism, we mean the triangle is the base. With a cylinder, the base is definitely the circle. And so when you look at it from the top like that, you realize that it's sitting on the circle, there's its base, and its face are both circles. And that's what makes it a prism, although we normally refer to this one as a cylinder. A cylinder is a prism. Its base and its face are the same, and the height of the prism is the distance between the two circles, so that's 6 centimeters. This is one of the most practical topics we study in mathematics in grade 9. And I'd like you to use the shapes that you've created along with any of these household type objects that you might have around you, so that you can make it as real as possible. I'm going to teach you formulas, and you can remember formulas off by heart, and that's also okay. But if you can make this real for yourself, with real physical objects, you're going to enjoy the topic a whole lot more. I hope you do.